Hello, everyone. Wishing you all a very happy new year and welcome to the first webinar of Nullcon 2021. Firstly, I would like to apologize for yesterday. There was some miscommunication and due to the difference in the time zone, we were not able to get Natalie to join for the yesterday's webinar. And it would just not be possible for her to make it on the short notice. So apologies for yesterday. Saying this, let's move ahead. Many of you are now used to attending a lot of online events in your own comfort zone. So we have scheduled our first Nullcon conference and training session in March 2021. If you would like to upgrade your technical skill set in web app security or kernel exploitation or even fuzzing, we have it all covered for you with our trainings. Today, we have a very special guest and a speaker, Natalie Silvanovich, who's a security researcher at Google Project Zero. She's somebody who needs no introduction in the information security space, but I would like to mention her area of interest is mostly reverse engineering, Tamagotchi consoles, and she focuses on security issues for Android and iOS messaging application. Natalie is going to talk to us today about exploiting Android messengers with WebRTC. Some house rules. If you have any questions, please send them across via the Zoom chat. We would take them after the presentation is complete. Also, please keep your mic on mute and feel free to switch on your video camera so that we can see you smiling. So without any further delay, I would invite Natalie and request her to begin her presentation.
Great, thanks so much. Today I'm going to tell you a bit about exploiting Android messengers with WebRTC. So I'm Natalie Silvanovich, and I'm a member of Project Zero at Google. And I'm glad that my most important qualification as a Tamagotchi hacker was also brought up. But today I'm going to tell you a bit about WebRTC. It's a topic that I've been interested in for quite a while. In case you don't know what
Natalie, your screen is not visible, just let you know.
Oh no, let me figure this out here, one sec.
Sure.
So it says I'm sharing. I guess I'll turn it off and share it again. Oh, I see what's happening here. Let's try this one. Okay, can you see it now?
Yes, absolutely. We can see the screen.
Great. Yeah, so sorry about that. So anyhow, yeah, WebRTC is an audio and video conferencing library maintained by Google. And it's kind of, the biggest library that no one's ever heard of. It's used by all the major browsers and by many mobile applications. I'll go through the list later, but there's a Google Duo, there's Facebook Messenger. I think those are the two biggest ones, but there's really a lot. And I think the reason it's so popular is that it requires limited server infrastructure. Basically, add WebRTC to your application and not have to set up any servers and immediately have peer-to-peer video conferencing. And it's also multi-platform. So many other platforms, and they can all talk to each other. So before I start, I'm going to go through some WebRTC terminology so you know what I'm talking about. To start off, I use the word WebRTC a lot. And when I talk about it, I mean Google's libWebRTC. But there's also libWebRTC standard, and there are a few other implementations of it. But in this specific talk, I'm not talking about those. I'm talking about the Google one. Also, I'm going to talk a lot about integrators. And integrators are the developers or organizations that include WebRTC in an application. So, for example, Firefox is an integrator. They integrate it into, or Mozilla is an integrator. They integrate it into Firefox, and Facebook is a WebRTC integrator. And then WebRTC applications are applications that use the WebRTC library. And yeah, they're the browsers like Chrome, and then things like Facebook Messenger and like Discord is another example. So how does WebRTC actually work? Well, there's kind of two stages. It starts off with what's called signaling, and signaling is sort of out of the scope of WebRTC. The part that's actually part of the library is that you exchange two pieces of information to set up a connection. And how these pieces of information are exchanged is not defined. So basically, if you're in a browser, you'll usually use WebSockets. If you're using like a messaging application, it'll usually be exchanged using the encrypted messaging format, but really just whatever is available. And then what happens is after this information's been exchanged, the two peers start exchanging media. And then this is typically a direct connection of audio and video routed from one device to another. And this diagram says browser, but this can definitely be a mobile app as well. And what are the protocols that are used? Well, this diagram on the left has what's typically used for signaling. So it's usually, it needs to be reliable, so it's usually over TCP and TLS, and it'll often use HTTP or WebSockets. But then once that setup is done, the actual audio and video tends to go over UDP. And sometimes, two UDP devices can route traffic to each other over IP. And if that's the case, then stuff will just go over UDP. But sometimes devices are behind a NAT and they aren't routable to each other. So then the ICE and return protocol will be used to basically create a routable network path between the two devices. And then typically WebRTC content is wrapped in TLS, and then audio and video data is sent using a protocol called RTP, real-time transport protocol. And sometimes there is SRTP, which is just encrypted. Yeah, and this is used for the data types that allow loss. So, audio and video, if you lose one frame, no one's going to notice anyhow. But then there's also data channels which are supported. And this is like if you're doing video conferencing, but you also want to send messages to the other person. Like, maybe the Zoom messages you're typing right now are sent using data channels. And this uses SCTP, which is a reliable protocol. So everything you send is guaranteed to be sent to the other end. So I've spent a couple of years looking for vulnerabilities in WebRTC now. And I've reported quite a few. And all of them were memory corruption in RTP. So memory corruption in processing audio or video. And when I first filed them, I just assumed that they were exploitable, but if they were exploitable, you had to pick up the call. If someone called you on a messaging client and wanted to exploit WebRTC, you would have to answer that call. And then I saw this story in the news. This was an exploit that was used by NSO Group against WhatsApp. And this actually was a fully remote exploit. And what they did is they had a video call, and they would use a bug that made it so that the peer-to-peer video protocol was moved forward so that it would happen before the call was answered. And then they would basically exploit a bug in that and then get code execution. And while WhatsApp doesn't actually use WebRTC, it uses an alternative called PJSIP. This made me wonder, whether it would be possible to use WebRTC to do a fully remote exploit. And so I started to look into this, and there were kind of three questions. The first question was, are WebRTC vulnerabilities exploitable? And I limited this to the Android platform. And then I wondered, how to exploit them. And finally, I wondered, if I did get a WebRTC exploit on Android, what could I do with it? Would I be just stuck with the application I started with, or could I use it on a lot of different applications? I started off by looking at some RTP bugs. I found two when I started this research, and they were heap corruption bugs. and I wanted to see if I could exploit them. And neither of them, honestly, were very good bugs. They both had limitations. They both had limited write size when you overflowed a heap buffer, and also they had limited write contents. And they were made more difficult to exploit by the fact that Android uses a slab allocator. So some heaps will have inline heap metadata to manage allocation, that if you overwrite a heap chunk, you might be able to overwrite that metadata. But it's not like that on modern Android. Instead, there's slabs that have allocations all the same size, and all the allocations are just next to each other. This meant that I have to overwrite something that was actually allocated by WebRTC. And in the end, I was able to use these bugs to very unreliably set the instruction pointer. And basically the way this worked is there's like tons of vectors for various things in WebRTC. And some of them have C++ objects in them that have these tables. And sometimes they iterate through them and make virtual calls. So if you have like a really bad heap vulnerability, sometimes you can overwrite the end pointer of the vector, and then when it iterates, it'll go out of bounds. And then you can like replace the table on the heap and set the instruction pointer. But this was like not great. It was not very reliable. But more importantly, I couldn't break ASLR. I could set the instruction pointer to 777, but not much that I could do next. So I decided I had to move on to bigger and better bugs. So I started looking at SCTP, which is the lossless protocol used for data channels in WebRTC. Historically, it had some out-of-bounds reads. So I looked at it and I found this really remarkable bug, quite an unusual and powerful one. So basically, WebRTC uses a third-party STP library. And this library can run over many transports, and it also supports custom transports. And that's what WebRTC needs to use because it wants to do SCTP over DTLS. And the way it works in the library is that the address is considered like a void pointer. And what developers are supposed to do is like, if it's IP, you put the IP address as that void pointer. Or, if it's like IPv6, it'll be an IPv6 address, something like that. But what WebRTC did is they actually put the real pointer to the transport as the network address. And this got like sent in all sorts of packets. So I discovered that basically during normal use in WebRTC, there were heap pointers being sent over the network like all the time, every single connection. This meant it was like really easy to get a heap pointer. But what was more interesting about this bug was that sometimes SCTP will do this thing where it sends a packet and then it echoes the packet back and it gets used. And it turns out the way this worked is when the packet gets echoed back, they would extract the pointer from the packet and do a virtual call on it. So this bug could also be used to basically very reliably set the instruction pointer as well. And there's a bit of a caveat that when you do this packet echoing thing, what was supposed to happen is that this packet is signed and it shouldn't use the pointer unless it's signed. But the signing ended up being really weak. Its key was generated with basically C-rand of the PID of the process. And there's not very many possible PIDs on Android. I think there's about 30,000. So this was like really, really easy to guess. So here's the code of this bug, just to make it super clear what's happening. The code that they used to have is just they would cast the address to the transport, and that would be the structure they would use. And like the right way that they should have done this in the first place was to use a map. So now they actually assign an address to, like a numeric address to each transport, and then when you use that address, they retrieve the VLC structure from the map. So after this bug, I was wondering, have I broken ASLR yet? Is a heap pointer sufficient to break ASLR on Android? And, I had a lot of things that I was going to put on this slide, and then I decided just no. No, on modern Android, that is not going to work. I looked at this a lot, and, with lots of heap histograms and that sort of thing. And currently, there's not any relationship between where the heap is and where code is on Android anymore. So this was not enough. I needed another bug to break ASLR. So I found this bug. And this was a funny story. I found it by code review by looking at the version of the STP library in WebRTC. Then I wanted to report the bug, and I discovered it had already been reported by another Googler called Mark Woodrick. But the bug was still in WebRTC, so I figured it was fair game. So this is the bug, and it's also an interesting one. So basically, this is the processing of an incoming packet for SCTP. And the way it works is you'll get the incoming packet, and then it has to reply to this packet type. So it will allocate an outgoing packet. But then if there's something wrong with the incoming packet, it will free the outgoing packet. Then it's supposed to return, but the bug was it didn't. And then it would send this packet that had already been freed. This was a great bug. You could basically fill this packet with anything and get it sent back to the client. But I also want to reflect a bit on this code here. Like the green plus is what got added to fix the bug. And this is, very subtle, very easy to miss. Who among us has never made a mistake like this? And this just shows how hard it can be to secure something with this amount of complex code. So I wanted to use this bug to reveal memory, but I had a few challenges. One was, once again, I was working with that Android slab allocator. And unfortunately, this packet had a specific size. And then OpenSSL loved allocating chunks that were also that size. But also, the chunk will get written when it's freed. And unfortunately, with these OpenSSL chunks, if that happened, it would get stuck in a loop, and then OpenSSL would never receive any more data again. And the only way to recover from this state was to actually restart the application. So that was no good. So I decided instead to try and put all the exploit in a single packet. So SCTP supports chunks. So basically, there's different chunk types that will do different things or contain data, and you can have more than one in a packet. So what I did is I made this long packet where first it would trigger the use after free, and then it would, process the chunks, would allocate the memory to replace the packet before it got sent. And this was a good solution because then I would get this packet, and then the exploit of this vulnerability would happen, and it wouldn't actually do anything with OpenSSL so long as I didn't send any more packets until after this had been processed. So these are the kind of the two features I ended up confusing. So I had this packet structure, and the important part is the data, and I was able to confuse it with this other stream reset chunk type, and then basically the sequence number and the TSN would be the data pointer. And this is a bit challenging because you can't quite set those to anything, but with a bit of shuffling and sending a few extra packets, it's possible to set them basically to a pointer value. So then, if I can read pointers, what pointers should I read? Well, obviously the one that they accidentally leak over the network, which happens to point to a C object. And then that gave me the location of a V table, and that finally broke ASLR. But then I realized I could read as many times as I wanted. So I also decided to read the location of malloc from the global offset table because, you might as well if you can read memory and save a few steps in the exploit. So then I wanted to set the instruction pointer using this ability to set the pointer to an object that gets a virtual call on it. But to do this, I needed to kind of create a fake V table. So my goal was to set this pointer to something that looked like a V table, but actually when you make a call, it has a pointer to some ROP that calls system. What I ended up doing was using what they call partial SCTP data, which is like if you've ever looked at IP, it has fragmentation. So you can send like half a packet and then send the other half of the packet. And I found out that an SCTP, that fragment data that isn't complete yet is stored in a pointer on the same object that I happen to have the heap pointer sent over the network to. So basically what I did is I would, send half a packet and then use this bug to read out the location of it. And that would be the location of the populated data for my fake object. Now this does have a problem because, if I am filling up the data and then reading the pointer, I can't have a self-reference in there because I don't know the pointer yet. So I ended up doing a thing where I would get this allocated and then set the value and then kind of free it in a way that I knew it would be allocated in the same spot and do this a few times so that I would know where the pointer was when I populated it and the thing could have self-references. So now that I've done the exploit, since I've kind of described a lot of things, I'm going to quickly go through what the full steps for the exploit were. So this exploit will first figure out the key that's needed to sign packets by basically comparing something that the exploit generates using rand to a random number that is put in a certain chunk, and basically you can crack the key that way just by guessing, and it takes less than a second. Then the bug reads the vtable and it reads the location of malloc, and then ASLR isn't a problem anymore. We know where everything is. Then this fragmented data is set and it needs to be massaged a few times so that it has a fake vtable in it and it can have pointers to itself. And then I set the IP and then it'll do then I set the pointer to the object and trigger the second bug, and then that will make the call to the gadget, which will make a call to system, which pops calc on an Android application. So that's how the full exploit works. So my next step was to see, I had this working on a sample WebRTC application, but could I make it work on a real application? So I scanned Google Play for APKs, including a string that is included in WebRTC. And I found 200 apps that use WebRTC that have more than 10 million installs on Google Play. That's actually a lot. But then I went through and I only found the ones that kind of had a plausible attack surface. So I didn't look at browsers just because on WebRTC, or on browsers, WebRTC bugs are not fully remote. You have to go to the web page, which means they're basically, one click like any other browser bug. So that's still concerning, but there's already a lot of research done on browser vulnerabilities. So I also removed applications that do streaming. And that's because fitting a WebRTC bug in a streaming application is also difficult. Like, for example, one of these applications is YouTube. And the way YouTube works is, you upload your video and then other people stream it down, but it's actually YouTube that generates the RTP and the SCTP. So for an attacker to actually use this bug to compromise, say, the YouTube app, they'd need to compromise the server. And that could be possible. There's definitely been bugs in open source versions of this type of WebRTC server before, but that's not something I investigated as a part of this research. Also, WebRTC is used a lot for projection. So you can have a mobile application and it'll use WebRTC in your desktop browser so that you can project the screen of the application to the browser and read the text larger. But that's not interesting either from an attack scenario, because if you own the device and you own the desktop, do you care that your device can compromise your desktop? Maybe not really that much. And also chat roulette. There were tons of chat roulette applications where you press a button and you talk to a random person. And this exploit was a concern, but I couldn't find a viable way to test them. you know, if you press a button and get a random person, that means like I can't press a button and get a device I control. So I removed these ones kind of due to a lack of text testability. So with all those removed, there were 14 applications that I thought this exploit could work on. And yeah, this is basically the list of the top WebRTC applications. And yeah, there's some fairly high usage ones in there. You know, 31 billion user applications, 500 million user applications. Yeah, very well used library. So I wanted to test the exploit on these, but I had originally written this exploit by altering WebRTC and recompiling it. And I thought this, you know, wasn't a valuable way to test this exploit on a lot of different applications. So I rewrote it in Frida. Frida is, I guess, a test or a debugging tool that you can use on Android and a lot of platforms. It allows you to write Python and JavaScript that hooks different methods and like replaces their functionality. So I wrote a Frida script that altered outgoing HTTP packets and analyzed incoming ones in Frida JavaScript. And this ended up being like a huge application. It was 1,600 lines of JavaScript to make this exploit work. But it was nice because I could basically plug it into anything. So I ended up having to hook 7 methods in each application to make the exploit work. It doesn't matter what they are, but I just want to mention that this was like a valuable number. It was reasonable to go through each application and find like 7 code points. So some of the applications, they had symbols, so I could just hook things directly. Otherwise, you know, I'd have to use IDA. Sometimes I'd look for specific log entries, and then sometimes I'd have to like trace up to find a specific function. Some of the functions had unique code features, like there's only one situation in user HTTP where a function is called in an if statement. So that's the sort of stuff I looked for. And I would say it maybe took me 20 minutes to analyze each application to be able to hook this script to it. So then I tested the exploit. It took on 6 applications. Most of them just needed modification of the vtable offset. So one numeric value had to be changed in the exploit. Some were fully remote and others were not. And the reason for this is application design. A lot of applications, when you make a call, they'll actually start the connection before they even notify the callee. And this like makes it really fast. You know, you pick up the call and then you can talk to the person right away. Other applications will wait till the person picks up the call to start the connection. And this is slower, but it's much more secure because it makes these issues not fully remote, and it makes them less effective because, you know, think of all the calls on your phone you don't answer. That you know that it's the difference between being able to attack anyone anywhere and kind of being able to attack anyone who will pick up the phone. So the exploit does need the data channel feature enabled, and this was the major reason it didn't work on some applications. Some of them had successfully disabled the data channel. Others had not. Even though it was disabled, I could, as an attacker, reasonably enable it. Also, like I mentioned with streaming, some of these applications use intermediary servers. It's actually fairly common for, you know, something like Discord, where, you know, one person is giving the video and maybe 100 people are watching. That's hard to do peer-to-peer, so there'll be a server. And then that means that if you send malformed packets, it'll only be handled by the server. So here are the things that the exploit actually worked on. For Google Duo, GeoChat, Signal, and Mocha, I was able to get a fully remote exploit. And then there were 2 social networking apps, VK and OK, where it was a one-click exploit. And you also had to have the user in your contacts, which was actually another great reduction in how useful this exploit was. Now I'm going to show you a video of the exploit being fully remote. this is Google Duo, and the left device is the attacker and the right device is the target. And note that I don't touch the right device at all other than to show the version. So you can see I've determined the key here, and then it's going to start reading the memory. Yeah, so you can see I've got the vtable, the location of malloc, and now it's populating that data structure. And there we go. There's the calc with no hands whatsoever. For purposes of comparison, I'm going to show you this other demo. This is for VK Messenger, and this is one click. So I actually have to pick up the call. And just look at how long I have to stay connected for this to work. It's going to take quite a while, and I think it would actually be reasonably difficult to find someone unless you social engineer them and to have them actually answer the call for this period of time. So just to show that defining applications in this way will actually deter attackers a lot. So I think we need some music here. Okay, there we go, finally. So as I said, when I looked at these applications, I figured out some ways that applications could reduce their risk. Definitely the combination of starting the connection after the callee answers the call, alongside only allowing people to call people who have them in their contacts, made this bug a whole lot less useful. Also, there were a bunch of apps that it didn't work because they disabled SCTP. And while they kind of got lucky here, this is generally a good design practice. WebRTC has a ton of features, and the more features that someone disables if they're not using them, the more protected they are against every vulnerability that occurs in WebRTC. So it's important that apps really only enable what they're using. And finally, I looked at these 14 apps, and 12 of them had not updated in a year, and that was very concerning. So the other important thing is that WebRTC applications should be updated regularly because all of these bugs have been fixed. But if you don't update WebRTC, you're not going to get the benefit of those fixes. So yeah, in conclusion, it was possible to exploit these bugs on Android applications, and it worked on many applications and was fully remote in some situations. Though the impact of the exploit depended on the app design. And well, a lot of apps were fully remote, some were not. And finally, I just want to end by acknowledging that one thing I learned from this research was that including WebRTC in an application is a serious security risk. And of course, there's lots of applications where video conferencing is a transformative feature, and it's really important, and it's what the app does. And I think in that case, WebRTC is a fairly good solution. But then there's a lot of apps that kind of include it and no one really uses it and it's not an important feature. And in that case, I think it's important to think about whether it's worthwhile introducing all this high-risk code. So that's it. I think I've got time for questions now. Thanks so much for listening.
Thank you, Natalie. Friends, if you have any questions, please send them across via the Zoom chat.
Let me check the chat here.
There aren't any questions.
Let's see. Yeah, can I share the slides? Yeah, sure. If you don't end up on the YouTube channel, just hit me up and I'll tweet them.
Yeah. I have one question, Natalie. From I think the list of 14 apps that you tested, which implemented WebRTC, which of the apps do you think they used the implementation of WebRTC in a much more secure manner to reduce the risk?
Yeah, well, it was really those two social networking applications who did it the best. And I should mention that Signal, after this research, did improve their usage of WebRTC a lot. So now they've implemented the contact thing too. So now, if someone who you've accepted your messages before it calls you, it'll work the same way it does and start the connection right away. But if someone you don't know calls you, it'll actually make you press a button to say it's okay. And that is the same effect as basically the contacts thing and also the delayed connection in the social media apps. So I think those are the three now that are in the category where I think they do it very securely. And I think the other ones could be improved. So got a question here. Can we still execute this exploit as POC, any link or repo? So I did a blog post about this on the Project Zero blog, and I think I have a link there. But the actual exploit source is linked to the bugs in the Project Zero bug tracker, so you can find it there. But yes, so it won't work on these applications. They've all been fixed. But if you want to use it on an old version for learning purposes, yeah, the full source is available.
All right. Any more questions? Well, either the audience is completely amazed or it's too much for them to digest at this point of time. But anyways, Natalie, thank you so much for this amazing presentation. And we will record this webinar and upload it on our YouTube channel as well. I will also post the links of the Google Project Zero link where you have mentioned about the exploit in the blog post.
Sure thing. Afterwards, I'll send you the exact link. And yes. Also, I put up my contact info at the end. So if anyone thinks of any other questions, feel free to get in touch.
All right. Thank you so much, everybody. And do join us for our upcoming webinar, which is scheduled next week onwards. Thank you, everybody. Bye.